Good afternoon, everyone. This is Katrina here at the Passivhaus Alliance United States. Welcome to today's webinar. We have Graham Wright, the Phius Senior Scientist, here to do part 2 of the Introduction to Phius Plus 2015. Please save the date later this year, September 9th through 13th, for the National Passivhaus Conference right here in Chicago. Thanks to our platinum level sponsors, Building Science Corporation and Rocky Mountain Institute. Thanks also to the silver level sponsors, Mitsubishi, Marvin, and Casella Dorkin. And we hope you enjoy this member benefit project of the Passivhaus Alliance United States. If you can give me just 1 second, I will pass the controls on to Graham.
How is that looking?
That's looking great. I can see your first slide.
Very good. Okay. Yes. So, hello, welcome everyone. This is part 2, and might start out by reminding people that so this was a report to Building America, or funded by Building America, and so the objectives that we wrote for the report were, yeah, we want to look at this idea that if we came up with climate zone specific performance criteria for heating and cooling in a cost competitive way, that would guide designers towards passive measures in proper balance with other conservation measures. And that was definitely that first objective was definitely part of the plan all along. The second objective kind of got added as we went along, and I'll explain more about that as we get into it. And kind of the way that we framed this for the final report there is that, and you know, the reason why Building America was interested in this in the first place is that you know, all of this is, if you look at it from a high-level perspective, people are talking about the same thing for quite a while. So there was what I call different Passivhaus incarnations here. There was you know, the first generation in the 70s and early 80s. The super insulators and the micro-load passive crowd, and then what you could call the second generation PHI's work in the 90s and up through today, but also you know, the DOE Challenge Home, and it's now called Zero Energy Ready. It's you know, they rebranded it as Zero Energy Ready, but it's not actually a net zero badge. You know, it's about all the things that you do to get ready to put PV or to go to net zero. So that's all the things about the building envelope and the efficient equipment that's in it. And then so we're proposing basically you know, Phius Plus 2015 as the next generation challenge home. That was the impetus for the study. And really, the key difference here is the issue of, well, how, you know, all of this is about really, you know, reducing the heating load, or the heating and cooling loads in the building. How low is low enough? How low should we go? But there are other, and it turns out there's other kind of important differences in terms of style, whether there's a prescriptive emphasis or a performance emphasis, whether there's any consideration of total energy in addition to the heating and cooling, and what is the approach to quality assurance. So those first generation folks, yeah, they had a somewhat flexible idea of how low they were going to go, and what they talked about was, well, we're looking for a peak load or system capacity reduction, furnace size reduction, 60 to 80%, maybe an 80 to 90% savings on the annual heating bill. And there were other concepts, like related concepts, sort of like point source heating sufficient. and so it really was a mostly a performance concept, although they, the package of measures that they came up with is the same that we talk about today. The super insulation, the air tightness, the good detailing, heat recovery, ventilation, all, and a modicum of solar gain. But they're, they had enough to worry about with just heating and cooling. They didn't really address the other forms of energy use that go on in the building, and the quality assurance was mainly a matter of craft. So as Katrine explained, North America kind of dropped the ball. PHI picked it up, and they did a number of things. They added an annual source energy limit to their standard. They made air tightness a high-level pillar, added ventilation commissioning, and they set this, and they drew a line in the sand on how low you should go quantitatively with the heating performance, and that was either this 10 watts per meter squared peak load or 15 kilowatt hours per meter squared annual. So the challenge home, that's different. That also addresses total source energy, but it's HERS rating before PV, and the quality assurance is different. Instead of, they added extensive checklists for that, and their prescriptive performance thing is kind of both. They have both paths, but it's much less aggressive than what the what the PHI is looking for. So, and to kind of summarize where we ended up with our recommendation, we were again looking for something like a 77% reduction in the peak loads and peak heating load, and 86% reduction in annual heating bill. That's kind of how the median numbers came out. Again, it's mostly a performance metric or performance criteria. We're going to retain the annual source energy limit, and Phius had already adopted the extensive checklists from the DOE. What else did I want to say? Yeah. So another thing to mention is the idea of the the original ideal, I guess. This notion of the furnace-free house that was already present in the first generation thinking there. But as Katrine mentioned, we found that the argument that was being made for the criterion, the 15 kilowatt hours per meter squared and 10 watts per meter squared, that was an economically optimal point to set the criteria. We found that wasn't working out, and it became clear to us that eventually we could choose to define the space conditioning target as a design for a really low peak load, or by an economic optimum, but not everywhere at the same time. And just to review this a little bit, so this was this is the argument that's made for how low to go on reducing this this annual heating demand, is that if you reduce your heating bill, you're saving energy and therefore saving money, but you're putting cost into the envelope to do that. So when you annualize that cost, there's an optimum point where your annualized costs are minimum. And now it turns out, so this was kind of the general argument, and specifically, PHI determined that this was where they wanted to set it for their climate and their cost structure. Turns out the U.S. government developed like free software for doing exactly these kinds of calculations, and a cost database for doing these kinds of analysis. And so the graph, the swoosh graph there is basically the same graph, except that it's turned around, and instead of instead of zero use on the left, like zero use or 100% savings is on the right. But yeah, we noticed that there's, we've got this tool that we could use to look at this. And so, yeah, so PHI they came up with a definition, or they said, okay, yeah, we're going to define a passive house as being basically a building that you can heat just through the ventilation air. Supply air heating sufficient and cooling. And what that leads to is pretty quickly, let's see, that's not showing up. Oh, there it is. Okay. Yeah, so what that leads to pretty quickly is, yeah, we need a little bit, we need this much air per square meter of floor area. So we've got a certain ventilation airflow rate that we have to supply. There's a maximum temperature rise that we can put on that before things start to burn and smell funny and stuff like that. And then there's the heat capacity of air. So that pretty quickly gets you to a very general and universal limit of 10 watts per meter squared. Let's back up. And kind of the argument was that, yeah, right at that point where you can now put all of your heating capacity into the ventilation air, then we can get rid of the heating distribution system, which saves a lot of money if it's hydronic, and so we do this kind of tunneling through the cost barrier thing. But then, instead of just sticking with that, they said, well, you can certify either on that peak load or on an annual heat demand of 15 kilowatt hours per meter squared in a year. And in Europe, they were already accustomed to writing building code this way on annual energy use intensities. So yeah, it turned out that, yeah, if you took a building that was designed for 10 watts per meter squared and you integrated its heating over the season, it came out to 15, and so they said, yeah, that's an alternate criterion. We'll let you certify either or on that. But the problem was when we started applying this all over the place in North America, we found out that it didn't work out that way. You can kind of understand, or it's pretty clear that an annual heating demand is going to have a lot to do with the degree days, and the peak heating load is going to have a lot to do with the peak design temperature, and those two things are not correlated all that closely. If you get away from the coasts, you have relatively harsher peak design conditions, and so the consequence of that was that this alternate annual heat demand criterion was almost always easier, and therefore most people, when they went for certification, used the alternate annual heat demand criterion. People certified under that, when we look back in the database, 92% of the time, if you're outside of the marine zones 3C and 4C, and only 42% of the time within those zones. And that was kind of, that became a problem because you can push down the annual demand with a lot of solar gain, and that was leading to these a tendency toward overglazed designs. And so it's very interesting. So in 2012, PHI came out with a report, and it seemed like they were going to hang their hat on this 10 watts per square meter thing. So what they've done is they've taken their townhouse or their townhouse end unit study building, adjusted its upgrades so that every point on the graph there is a 10 watts per meter squared peak load design, and then they show this plot of what the annual heat demand is, and it varies, you can see, from like 1 to 50. And so they kind of penciled in this, this criterion here, the pink line there, where, yeah, it would be at 15 kilowatt hours per meter squared a year, but, you know, if it got, when you get into the colder climates, it would ride up. And they did kind of a similar thing looking at the cooling side, the annual cooling demand. Added a budget for dehumidification. So this characterization parameter they've got here, that's sort of a combination of the annual average temperature and the dehumidification degree hours. They went ahead and implemented this cooling one, but not the heating one. As far as I know still today, and I saw, you know, in their press release March 19th, they're sticking with the 15 kilowatt hours per meter squared and year everywhere. And I believe that the reason for that is kind of illustrated by these climate comparisons here. So I think Katrine touched on this a bit, yeah, if you look for places between Central Europe and the U.S. that have kind of similar heating degree days, you'll find that in the east it's a bit colder on the peak load, or a bit colder on the design temperature. Things cross over pretty well in the Pacific Northwest. You know, we've got pretty similar heating degree days between, say, Frankfurt and Squamish. Portland's easier. But if we go away from the coasts into the middle of the continent, you know, all of these places have pretty similar heating degree days to Central Europe. But the design temperatures are much colder, so it's going to be very difficult, you know, relatively much more difficult to design something for a low peak heating load, a 10 watts per meter squared peak heating load. You'd have to go south almost to Nashville to get a comparably mild peak design temperature as to Central Europe. And when you do that, you have less heating degree days. You have a shorter heating season, and that means it doesn't pay back as well. Out west, pretty similar, maybe even worse. Or yeah, you've got quite at the same heating degree days, you've got much colder design temperatures, and so this does make designing for that supplier heating sufficient level, you know, very difficult in the mid-continent areas or away from the coasts, and you can see that would enter into the economics, because it's really the annual savings that have to pay back that extra investment in lowering the peak load. So these harsh conditions that we have, which are very characteristic of the mid-continent U.S., are not conducive to design for supplier heating sufficient. And so we concluded that this was not fitting well everywhere, and needed to be relooked at. And so we're promising. So we're going around promising that yes, this is economically, you know, feasible or economically optimal, but that promise is not. We're not delivering on that promise, so we need to redeem it, and still deliver on the promise of really deep energy savings, and the thermal comfort and the resilience. You know, we want to maintain all of want to still deliver on all of these things. And so we said, well, yeah, that's if we do that, you know, we're gonna end up coming up with different numbers than these. And so this is what we set out to do: cost competitive passive building standard for varying climates. So to back up, to zoom back out a little bit here. So from the point of view of so we've been practicing the Passivhaus standard from PHI, and from the point of view of what we're gonna keep and what we're gonna change, we said, okay, well, we still want it to be performance-based. We're not going to go prescriptive. We're not going to try and do outcome-based. We're going to keep it pass-fail, and the same criteria are still going to apply to all types and sizes of buildings, except for special allowance for commercial process loads. And we're going to keep the same three pillars: the limits on space conditioning, limits on total source energy, and a separate air tightness criterion. And what else did I want to say? So yeah, so much has been made, I guess, of the on this all types and sizes of buildings. There's been maybe quite some commentary on our choice of the 2,000 square foot single family detached house as the reference study building, that this somehow incentivizes that particular building form. That's mostly not true, because the criteria are the same for different sizes of buildings. The surface to volume effect still plays there. So it's still even if you move or shift the exact type of building that you're centering the study on by a little bit, from a townhouse end unit to a smaller townhouse end unit to a larger but detached single family house. Even if you shift that center point a bit, when you go much smaller or much bigger than that, the surface to volume effect still plays in. So larger multifamily projects that are more, that you would say are maybe a better idea because they're more efficient with materials, and smaller detached houses or strung out designs are that are less materials efficient. Those are going to be more difficult to design. So in terms of incentives, that for different sizes of buildings, it all pretty much works the same way. So yeah, so we kept the three pillars, but I want to kind of suggest a different list of three things. Is a good way to think about this, and that's 3 hurdles to net zero. So the first hurdle is you got to meet the space conditioning criteria, and that is about reducing the load on the heating and cooling equipment. And what this does is it puts passive measures first among conservation measures. And again, we also got commentary around, well, what are you calling a passive measure here? It's not, it's not passive unless it's completely passive. This kind of objection. But we're including in the passive measures list the same kinds of things that have been in there still. So like an HRV is considered a passive measure, even though it does have a motor in it with wires running into it that it needs to run, and that is because those things have a lot of leverage. With just a little bit of energy input to run a fan or a pump, you can recover or harvest a lot of low-grade heating and cooling from the environment. So they can have pretty high coefficients of performance if you look at it that way. And so those are considered inside the tent in terms of things that can be deployed to reduce the heating and cooling loads. So the second hurdle is that there's a cap, or there's a limit on the total source energy, and that is about reducing the load on the grid, or the impact on society. And so now you have to deploy things like efficient equipment for the heating and cooling. So first you design the envelope and the passive measures to take the load off the heating and cooling equipment. Then you use efficient heating and cooling equipment to get the load on the grid down, and what that does is it puts like the whole list of conservation measures ahead of renewables. Although we did, so one of the features of PHI's Passivhaus standard was that solar hot water counted as an offset, so the tech committee decided, well, we're going to put PV and any other renewables that you might have, micro hydro and so on the same footing there. So if you're generating electricity on site and using it at the same time that you're generating it, that's counted as an offset. So the limit of the total source energy applies net of renewable generation that's happening on site, produced and used coincidentally. And so then the third hurdle is, once you've got your impact on society down to that level, then third priority is to put even more energy back out onto the grid and net zero, and that's and that right now is that's an optional add-on badge. So, and there was another. So we tech committee decided also to add an additional add-on badge for this supplier heating sufficient idea. So, in a sense, we agree with PHI that is a good idea, but it's not actually required. But if you, for those folks that do have a copacetic climate for that, people in zone 3C and 4C are encouraged to go for that additional badge. Right. We also changed we made some changes to the way we look at HRV and ERV efficiency numbers, and we changed the reference floor area to an internal dimensions version of the condition floor area. So what's different is, from the point of view of looking at PHI's Passivhaus standard and the three pillars thereof, we reconsidered all of those three pillars, and according to different principles. So the space conditioning criteria were reconsidered on the basis of economics. We're looking to set the level of investment in passive measures and these low-grade harvesting measures at a cost-competitive level. And the source energy, we reconsidered that on the basis of the global impact. And the air tightness pillar we reconsidered based on moisture risk. So those were kind of compartmentalized studies or considerations. So I'm going to talk most of the time here on the space conditioning stuff, and try and get to the source energy maybe a bit at the end. So again, we've got this BEopt tool, and the way that let's see, how should I start out? Yeah, so the way that NREL, National Renewable Energy Lab, and set up their BEopt software to work is that really what we're looking at is a plot of source energy savings on the x-axis and annualized cost on the y-axis. And so we're going to start off with a baseline case, and we're going to add low-hanging fruit conservation measures, and and that'll increase the 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 amortized cost or the financed cost of the building. But if they're in the low-hanging fruit side of the tree, then they will save more energy, save more dollars in energy in utility bills than what they cost to finance, and up to that, up to a break-even point, or a minimum total cost point, which is 0.2, and then there may be some further, higher-hanging fruit measures that get you more energy savings, but give back some of the annual cost savings. And at some point, which is 0.3 here, they say, well, it would make sense at this point just to start adding PV, adding more and more PV to net you out zero. We take some issue, so we're going to use this tool, but not the way that they propose exactly here. And so what we did is we said, well, we're gonna look at 100 and some climate locations, and the list of locations basically is the list of files for which we have WWOOFie weather data, so that we can do like a full hydrothermal analysis if we need to. And so I came up with kind of a custom version of that swoop chart, or that annualized cost chart. And so just as with the with the raw BEopt output, I've got annual energy-related costs on the y-axis here, and then energy savings on the x-axis. Because it's an all-electric building, it doesn't actually matter whether it's site or source. Those are just proportional to each other. So that is what corresponds to the to this green curve is the green curve on here. And according to the calculation protocol that we set up, we don't dink around with a lot of low-hanging fruit. We're going to go ahead and make some upgrades right away, so that gives us a pretty good starting point. But then yeah, we go for some low-hanging fruit. We come to the cost minimum, and at some point, it becomes economic to add PV, and so there's an option for like a 2 kilowatt PV system for this house, and what we really keyed on for setting the criteria was the swoosh curve with the renewables edited out of it. So the optimizer, BEopt optimizer, had the choice of adding 2 kilowatt PV or a 64 square foot solar hot water, just to kind of see where those would come in versus the conservation measures. But what we're really interested in for setting the space conditioning criteria is the diminishing returns behavior of the conservation measures. So that's the blue curve, and all that is the green curve with the increments of savings and cost from the solar hot water and the PV going in, like edited out of the sequence. And so just for kind of relative comparison here, where we ended up setting, or choosing the criterion, or choosing where to stop in Chicago was right about here on the blue curve, and right about there on the green curve, and that's going a little bit past cost minimum, a little bit past PV start, and then rolling over into diminishing returns. So we stopped short of going for this one big step here, which is I believe that was like an upgrade to a 90% efficient HRV. And by comparison, the 15 kilowatt hours per meter squared would have been about up here, and to actually get to supplier heating and sufficient in Chicago would have been off the scale. So we made, so there's a number of assumptions and constraints that go into setting up these cost optimizations. So we said, yeah, what we're used to saying in Passivhaus is that, yeah, people can tolerate a little bit colder air temperature because there's not a lot of drafts or thermal bridges or really cold surfaces on the windows. So we've got a fairly wide range of temperature set points. Also assume that people are on top of it in terms of using the windows for natural ventilation cooling, and that they're capable of putting up solar screens or shades seasonally to cut down on the cooling load. However, we are going to increase the assumptions about what people are using for lighting and plug loads. And in the studies, we also stuck with the Building America house simulation protocol for hot water usage, which is about 50% higher than the PHPP assumption. We're not enforcing that in certification, though. Also assumed that there's exhaust range hoods and exhaust dryers, and those, are operated in the same, as per what Building America house simulation protocol would say, and so that kind of cuts down on the overall ventilation efficiency, even if you have a pretty good ERV. I think Katrine covered or mentioned about the lighting and plug loads being kind of 80 or set at like 80% of ResNet, so again, here's our little archetypal study house. It's a 2,080 square foot exterior dimensions, 2-story house oriented short side south with neighbors on east and west. 3-bedroom, 2-bath, and we do, very importantly, constrain the windows, the window U values for comfort by climate. It's airtight. It's got ducts inside, and the window. So the optimizer is allowed to vary the window concentration on the south, or concentrated on the north, but only up to 40%. As I think I mentioned, we were seeing in certification too often, people were going for 50, 60, 70% glazing on the south side. And so in the beginning, we had a quite ambitious and grandiose test plan. And phase 1 of this was the economic studies. So the idea was, we're gonna move this building around 100 places, run these BEopt analyses, compute the optimal upgrade packages, compute that whole curve. But we're going to constrain it. We're not going to mess around with the air tightness. We're not going to mess around with low performing windows. We're going to make sure that we force a window upgrade to maintain a 60-degree interior surface temperature in the winter, and we're going to partially upgrade or educate the occupants, as noted above, and then what we're going to key on for the setting the criteria is this point of diminishing returns, and we're gonna make that a judgment call, location by location, as opposed to coming up with some kind of mechanistic formula or algorithm for it. And so once we see that point, we just write down the annual heating demand, peak heating load, cooling load at that point. And then this is the statistical smoothing. That was to fulfill the second objective that we added. These analyses in BEopt take quite a while. I think the average was 14 hours, and that's on like a 32-core Amazon cloud server. So we figured that wasn't really, feasible for day-to-day, certification work or design work. So we're going to take these location by location targets, and we're going to fit statistical models to them, so that we can extrapolate to other climates. And you can kind of anticipate that the annual heat demand criterion would have something to do with degree days, the peak heating load criterion would have something to do with design temperatures, and so on. There were a couple of other pieces to this that had to do with a couple of other ambitions that we had that got moved to future work. One is looking more closely into the thermal comfort issue. Wanted to do some dynamic modeling around the difficulty of heating and cooling distribution, and how to use comfort metrics to set criteria for both outage scenarios and for normal operation. Also, there's a bit of an issue here because BEopt is computing the peak loads, so our system capacities according to manual J, which is different than the method that's used, in the softwares that we use or have people, use to model projects for certification. So we need more data points on how those cross over. Right now, our rules or our conversion is based on a small number of data points in climate zone 4A. So we ended up deciding that we're not going to do the either or thing, because we're looking at the total picture, or looking at all these different climates separately. We really want to set criteria on both the annual demands and the peak loads, so that we don't let things get out of balance the way that this overheating situation developed with the alternate criterion. There was much discussion. Which is more important, the peak loads or the annual demands? And so we went for all of that. So let's see, 45 minutes. Okay. Gotta think about how much I can cover here. So again, the standard setting heuristic is that we're gonna go beyond the straight up cost minimum, and we're gonna go beyond PV start and get more savings, more peak load reduction. So what we're looking for is a point kind of just over the knee of the curve, where the conservation rolls into diminishing returns. The only exception to that is if your climate is really harsh and you're way over the source energy limit at the PV start point. We said, okay, you don't have to go beyond PV start, and that is to save some, basically to save some money to address or save some flexibility to address the source energy limit. And so this is just a screenshot of what the what the actual BEopt output screen looks like for the case of Chicago, and it's always comparing a benchmark to the upgraded case, and this happens to be the Wright 4743 optimal 24. Yeah, so this happens to be one of the points that got picked as where we wanted to set the criteria for Chicago. And so this dark red thing here, that's always the space heating, and then the pink on the top is the hot water. So yeah, we're crushing the annual heat demand pretty good there. And this big jump here is the 2 kilowatt PV going in. So we picked a point that was beyond the start of the PV. And the corresponding, my corresponding custom report looked like this. So and that point number 24, that optimal point that we picked, is right about there. So we're going to stop short of doing that great big HRV upgrade, but we're going to push past the strict optimum and get a little bit more savings. Give back some of the dollar savings, and get a little bit more. Try and get a little bit more peak load reduction out of that. Yeah, on the red curve here is the the incremental capital cost, or incremental first cost per square foot that we're asking for. Yeah, so I think I'll skip that one. So yeah, there's quite a bit of so the custom report that I built up for looking at the BEopt output. It's got the space conditioning performance, the % reduction from benchmark over on the left, and then there's a whole bunch of additional columns that show the total picture in terms of all the upgrades that the optimizer picked. And so yeah, so if you look at San Francisco, there's it's a heating dominated climate, but it's a milder one than Chicago, so there's not as much space heating savings to be had. And I think, yeah, PV works better. Probably this big jump. I think this big jump here was the PV going in. This one was the solar hot water going in. This one over here was probably the heat pump water heater going in. And so for some place like San Francisco, I would pick probably like either here or here as the point. Yeah, a little bit beyond the cost minimum. Here's the cooling dominated place, so there's very little or not a whole lot of heating demand in Houston, but there is quite a bit of cooling. And in general, as a general thing, it wasn't possible to get as much savings on cooling. There just aren't as many passive measures that deal with that. And yeah, even so, the optimizer was given choices of upgrading the thermal mass, doing extra drywall or concrete slabs on the inside, and usually those fell into the category of high-hanging fruit, even in the hot climates. Yeah, in Houston in particular, there's a lot of dehumidification load that basically the optimizer does not have a knob, it does not have a passive knob to get rid of. So yeah, kind of picked something like here for the Houston case. And then yeah, so this is Portland, right? Portland. And so that's also got a pretty significant heating load, and that's we're picking a point that's a little bit beyond PV start and crushing the heating demand pretty good there. So that would be the, again, yeah, stopped short of doing the next, upgrading to the super expensive HRV. And then, yeah, in a very cold place like Edmonton, yeah, they've got a huge space heating demand, but we're not gonna push them as far, even though the diminishing returns behavior did not hit the wall as fast in such harsh heating dominated climates, where we decided, okay, we're not going to push them quite as far, because they've got so much work to do on source energy, even after they've crushed their their heating demand by 90%. And so this is kind of, so we did these 100 locations, and this is basically a zone by zone kind of summary, or zone by zone median values. And so yeah, you can see the the space conditioning runs from up to maybe 13.2 in kBTUs, and the cooling runs the other way. And then in this column, basically these are the window U values that went into that, and some indication of the solar heat gain coefficient. It varied in some climates, and in other climates it didn't. Basically, the optimizer only had a choice of like low, medium, and high for window solar heat gain. And then this is what we achieved in terms of those percentage reductions, and I think these are still quite respectable. We're in the 80s and 90s for the space heating demand, and maybe in the 40s or 50s for space cooling. And likewise, the system capacity or furnace or air conditioning size reductions are also looking pretty respectable. So if you kind of just take the median over all the points that we studied, this is kind of how it came out. We managed to get something like an average 86% reduction in heating demand, 46 in cooling, and so these are, on the face of it, kind of similar numbers to what the what the first generation practitioners' idea was of how low to go, except that they were talking about reductions from pre-1980 conventional construction, and this is reductions from 2009 IECC. And there was actually a little bit of improvement in the code over those 30 years. And yeah, so comparing, I also compared this to what it would have been if we had just kind of mechanically picked these PV start points. And yeah, so we got more percentage savings on heating, a bit less on cooling. And so, you might ask, well, why are we pushing past this cost minimum? There's reasons to do that. Basically, we're doing the economic analysis here with very conservative or conventional assumptions about fuel escalation rates and inflation and discount rates, and these these assumptions might not be right. Every time there's a fuel price spike, your economics all of a sudden gets dramatically better. In retrospect, I'm quite glad that we didn't really place too much, didn't really key too much on the crossover point with PV, because that's that calculation is predicated on net metering at retail. That might go away. Also, you know, the things like the prices of PV and the incentives for PV are kind of unstable right now, or seem to be changing rapidly. And so, yeah, I think the procedure that we came up with of just focusing on the diminishing returns behavior of the conservation is a more robust way of doing things than comparing to like the exact crossover point with PV, or even worse with something like a cost parity to the cost parity point to the to the benchmark. Both of those are going to be like more sensitive to cost details. Another factor is that in this analysis, there's not a lot of credit being given for the additional resilience that the passive measures bring. It's assumed that the power's on 24/7, and so there's no consideration of the risk of outages or anything like that. So I do want to be forthright about this point, that one of the comments that we got back from the reviewers was that even if you didn't constrain your optimizer with these forced window upgrades, the cost minimum points that BEopt would calculate are still have paybacks that are too long. So that's a bit of a caveat here. So having run all these points, and in some cases, I should mention maybe that it was difficult to decide between a couple of adjacent points. Like, should I go for that next for that next more efficient water heater, or should I go for that next more efficient HRV? So each location actually got 3 votes, and in some cases, yeah, it was very clear which point to pick. In some cases, it wasn't. But yeah, we ended up with 100 locations and sort of 300 data points, and so now we're going to fit statistical models to our annual demands and peak loads, and this is kind of what the formulas end up looking like. So yeah, the specific space heat demand, annual space heat demand, that involves, that's basically, you start out with this much, and for every 1,341 heating degree days, you get 1 more kBTU per square foot in year. But there's a couple of takebacks. So it turns out that if you're in a sunny place, you can do better. That helps reduce your annual heat demand. So the brighter your climate is, you have to do a bit better. Also, the higher your electricity price is, the better your conservation measures, or the better that your heat reducing passive measures pay off. So there's a take back for high electricity prices as well. And but yeah, if you kind of look at the sensitivities on the same scale, the heating degree days is the dominant factor, and then the solar radiation and the electricity price are secondary effects. And the cooling, that ended up fitting pretty well to cooling degree days, dehumidification design, humidity ratio, and the interaction of those two things. people did ask or did point out that it's more common to look at cooling degree days on base 50 degrees. That might have, I'm not sure, that might have correlated better, but you know, the R squared is pretty good here anyway. Maybe next time maybe next round we do this, I'll try CDD 50 and see if that's better. And again, yeah, the criterion was mainly controlled by cooling degree days for annual cooling demand, but needed a bit of additional relief for the higher humidity places. And then the peak heating loads, that peak heating load was mainly controlled by the design temperature, as you'd expect, but there's also takebacks for electricity price again. So again, the higher prices, higher energy prices are justifying more upgrades that reduce the peak load on heating, and also there's a take back on from heating degree days. So you get some, basically you get some overlap if you're the same things that reduce your heating your annual heat demand also are good for reducing peak load. But again, yeah, the heating capacity is mainly influenced by the heating design temperature, and then the other ones are secondary effects. Cooling capacity, yeah, that ended up being the most complicated formula with this interaction term here. Basically, it needed, it was had a lot to do with both the cooling design temperature and the cooling degree days and the dehumidification and the interaction of them. And so again, we didn't get to looking into the comfort in great detail, but again, I'm mostly not worried because of once you've gotten rid of the drafts with your air tightness, and once you've done thermal bridge free construction, and then what's the risk factor to comfort? Well, it would be like low surface temperatures on the windows, and we've constrained that out of existence. I did run this is a 1-year dynamic simulation of the interior conditions in Chicago. Did this in Wolfie Passive Dynamic, and you can see there that, yeah, indeed the window temperature is staying up pretty good, and the only comfort problem that actually happened was there's in the climate file for Chicago, there's a spring heat wave, and that happened to occur outside of the time window when the cooling system was enabled. So probably that should be, at some point, that should be redone with like a longer cooling system, longer cooling season. So in summary, right? So it's got the same high-level architecture as it had before, as what we were practicing before, but we're proposing adaptations for all of the 3 main pillars, which we think are rational, and as to whether the new space conditioning targets actually deliver cost optimality or competitiveness, not necessarily. This is national average cost data and so on, but we're trying to get people closer and try to put an end to pushing people like way out on the diminishing returns curve, or letting people off too easy in mild climates. This is that was kind of a problem with, we thought, with maybe just setting peak load criteria, is that yeah, in in places like San Diego, that was too easy. And so, yep, we're leaving a uniform source energy limit in place so that everyone does their part for the planet or for society's impact. But really, the purpose of the space conditioning criteria, that's really benefiting the building owners and occupants, and so it's fair enough to recalibrate those for economic feasibility. And we expect the way this will play out is, because we're now requiring performance on both annual demands and peak loads, that more projects will probably encounter will find themselves limited or challenged by the peak load or the primary energy limit, instead of the just always being able to focus on the annual heat demand. And we do believe it will tend to favor higher occupancy and more efficient forms of housing, and discourage these underpopulated McMansions. Mainly because of on that last point, mainly because of the changes to the way we're dealing with source energy. Let's see. Maybe I'll just try and quickly say something about that. So, we didn't try to do anything super fancy here in terms of pricing carbon or avoided, or cost of avoiding carbon emission or anything like that. We're simply noting that there's a limit. The IPC says, yeah, we can emit about another yay much. If we want to, avoid, more than a 40% risk of severe and irreversible climate impacts. And so it seems appropriate to do something like an equal share calculation of that. And so, that would be something like 100 tons per person. Currently, U.S. running at 17 per year. And so if you say, well, only maybe a third of that is building sector, you come up with a kind of a per person number for the building sector of maybe in the neighborhood of 0.7 to 1.1, and we noted that the 120 kilowatt hours per meter squared primary energy limit that we had been working with is right about 1. So, and that's making just kind of like a linear glide path. Like, how much would you, if we're assuming that somehow we're linearly gliding to zero in 2050, how much could you emit this year? Well, about 1. And so we said, okay, well, yeah, the current limit is about consistent with that. But this is admittedly a different perspective on source energy than what BEopt is set up for. In BEopt's world, source energy is subject to economics, but we're saying no. We're going to say first of all, or to start with, it's not. It's just subject to a cap. Now, and if you wanted to be free market about it, or if you wanted to do cost of avoiding emissions approach to it, you could build a cap and trade system on top of that. But we're gonna start with this idea that there's a cap and there's that the atmosphere is a commons, and there's an equal share calculation underlying that. Let's see. I think, yeah, we'll skip a couple here. But we said, yeah. So we're going to, we know that our U.S. grid is dirtier than the European grid, so we're going to increase the source energy factor for electricity from 2.7 to 3.16, and consistent with this idea of equal share, or it's people advocated that the energy criteria should be per person instead of per square foot, and the total source energy, that's the right place to do that type of calculation. So for residential, you get a per person allowance, and the occupancy is determined by number of bedrooms plus one. So that's one of the things that's going to, that's one of the things that underlies this expectation that it will motivate design for higher occupancy. For non-residential, it's not so clear, what the whether that should be per person. So we're going to stick with 120 kilowatt hours per meter squared there. And as I think I mentioned earlier, there's partial credit for the fraction of renewable energy that's generated and used live on site, which puts PV on the same footing as the solar hot water has been. But we said, we have to do something about these lighting and plug load defaults. They're way too low in the PHPP, and so we're gonna increase that up. And that busts people. I think that was the point of this slide here, is that if we do, so just increasing if we look back in the database at the certified projects, increasing the source energy factor. So everybody was designing to the limit, increasing the source energy factor from 2.7 to 3.1, busted some people. But as soon as you increase the lighting and plug load defaults, everyone was busted. So we had to do some. We felt we had to put in some temporary relief. So if you just take the 120 kilowatt hours per meter squared and multiply that by the standard occupancy of 35 meters squared per person, you would come out with 4,200. And we said, well, we're going to, for the time being, we'll increase the limit to 6,200, but we want to put that on a glide path to back down to 4,200. And here's just an example of how the utilization fraction of PV would be calculated. You just compare your annual PV output to your annual electricity demand, and then based on some dynamic simulations, we generated these curves that say, well, how much fraction of that would be considered to be used live, or coincident production and use fraction. So this says that about a net zero size array would have something like a 38% live utilization. And so the change to the air tightness is again a change of scale from air changes per hour to CFM per square foot of shell, which keys more directly in terms of risk to the envelope. Uh-oh.
Hey Graham, are you ready to take some questions now?
I guess I am.
Great. First question from George asks, don't you think more effort should be spent on envelope design and less on math formulas? People want clear direction on the end goal, not as much on sausage making.
That's what the certification program does. Yeah, so this is just, yeah, the whole point of this was to of this talk was to get into the sausage making and what went into setting the criteria, so that so that you understand the logic behind it. But yeah, when it comes to actually helping people meet the targets, that's where your certification staff will help you out. I don't know if that helps answer the question or not.
Our next question is from Malini. She asks, or she says, there's a big jump in specific space heating demand from climate zone 7 to zone 8. Can you explain it?
This is maybe somewhat of an artifact of not having all that many data points in these zones. Yeah, the zones are not equally represented in terms of number of data points, and there's only a few. I think maybe only maybe 3 in each case. So yeah, if you went back through this and tried to do something that was more precisely population weighted or something like that, you might come out with different numbers. So these are just sort of general. This is just in here as kind of general indication. Again, these aren't, this isn't the approach that we took to like actually setting the criteria. It doesn't work zone by zone. There's the formulas are there to calculate the criteria for any given climate. So and zone 7 is pretty big. It covers a lot of ground geographically.
All right. John asks if you could expand on the assumed payback period that was cited as too long.
I am not sure what NREL had in mind for what's too long. I would only be guessing, but I don't know. Maybe everybody wants 5-year payback or 2-year payback.
Malini asks, have you compared modeled performance to the actual performance in certified passive houses, and what does that data show?
There is, I guess the short answer is yes and no. There's been data collected, but it hasn't been, not much has been done with it systematically. Adam Cohen on the tech committee has signed up now for to start looking into that. So we did some work on, we did some work last month on protocol on what we would like to see people monitoring kind of going forward. It's it varies. What's been collected kind of varies a lot depending on what people's goals were or what people's interests were. So we hope to publish more on that soon.
This question is from Jean-Francois. If automized window shutters have been considered for either residential and commercial buildings?
Oh yes, those are, yeah, that's certainly a valid thing to try.
Ah, he meant insulated shutters.
Oh, insulated. That, well, yeah. In terms of the standard setting study here, that wasn't an option that that was kind of incorporated as part of it. Um, but I know, you know, Thorsten up in Alaska is experimenting with that kind of thing, movable insulated shutters, and there may be other people that are trying to get that to work as well. Yeah, there's certain things I wish I had, or I hope will be, more available in the future. For example, like phase change materials. You can get that stuff right now, but it wasn't an option that I could study.
Okay, does anybody have any last questions? Oh, one more here. Regarding climate change, one, are there any plans to address it? And two, can you estimate coast times for heat and cold waves? And three, any suggested hedges such as wiring for auto shades, shutters, adjustable tidal PV?
Yes, I believe so. Okay, so as far as climate change itself goes, um, our one of our premises here is that yeah, if you design yourself a passive house, or with all these envelope upgrades, it's not only helping reduce your impact, it's also making you more resilient and robust to extreme weather events that might happen. Um, what were the other two parts of the question? Wiring for PV, or yeah, I think wiring for PV is that's kind of required by the checklist for the zero energy ready. Forgetting now the second part.
Yes. Can you estimate coast times for heat and cold waves?
Oh, not yet. Uh, that was part of the thermal comfort thing that we still want to get to, is to look more specifically at outage scenarios, and how uh, and how to prepare for those. One thing that concerns me, or that I would personally be trying to design for, is some kind of backup power for my HRV if I had one, so that I didn't have to necessarily open the windows. Depending on what climate you're in, definitely if you're in Chicago, you might think of trying to have some kind of a limp mode or hand crank for your HRV.
Okay. Jean-Francois asks, can you discuss more about source energy, the factor of 3.116, and how it is fair toward clean grid users?
Oh, right. Clean grid users are basically being required to share their bounty, um, and that that is uh, that is intentional at this point. Um, yeah, I had some discussion on Green Building Advisor with in response to the GBA article about our standard adaptation. That's what he was asking about. He's saying, yeah, in some regions, maybe there's what happens if there's 100% wind or something, or 100% cogen going on, so that you have very low source energy factor right in that location, or right for that particular utility or something. And kind of, we first of all, the tech committee did talk about that, and and essentially what we decided is, even first of all, it would complicate things. Definitely, if you're going down to the scale of individual utilities, then it's not just that utilities generation source factor that would have to be accounted for. You'd also have to adjust for their imports and exports, Um, so if you look at the larger interconnected regions, at least that problem goes away. But you still have differences. So then you've got something like a difference between a source factor of 2.3 or 2.4 for the western region versus 3.5 for the eastern. And so far we decided that we're just going to use the national average, and so people that are in clean grid regions, they don't get to take full advantage of their clean grid to increase their site energy. They're only allowed to do that to the extent that that it helps the national average. And after thinking about it a bit during the discussion there on GBA, I was kind of leaning towards the idea that, well, if we're using a number that's derived from a global cap, maybe we should be using a global average source energy factor as well, which would have the effect of sharing the benefit of any clean energy or clean grid project anywhere. That would be to some extent shared worldwide. Yeah. So it seems to me that or what I tried to argue back to the fellow that was looking for granularity there was, and it's going to a lot of trouble or going to a lot of complication to be accurate about local source factors. But then you create a fairness problem, and what are you going to do then? Are we going to then set up like a fancy trading system or something like that to fix that? It's easier or just more straightforward to do the sharing in the atmosphere itself, and that that I think is in general alignment with this idea that we're kind of all in this together on the climate front.
Okay. Enrique asks, has anybody developed a formula to calculate the cooling time without heat in an outage event?
Yeah, I mean, there's you can estimate a building time constant. If you've got a number for kind of thermal mass of the building and the average U value, it's basically the product of those or the ratio of those, and that's I think something we could come out. Yeah, you can do kind of back of the envelope calculations about that, but in order to really figure out accurately what's really going to happen, you'd have to make some assumptions about, well, how do my internal gains change? A lot of them go away when the power goes off, but the ones from actual people don't. So where, I think, how fast it changes, that's pretty much a property of the building. Where it actually settles to is also a function of what continues to go on inside the building. So yeah, I want to look at all that in more detail in the future here.
All right, our last question's from Tom, and he asks if you're planning to use future climate data.
Haven't really considered that, or haven't really looked into that. I think I'm hoping that it's not changing fast enough that we would have to, do it on a 3-year cycle, or we're definitely uh, looking to update this analysis um, every 3 or 5 years or so, to pick up changes in cost or uh, yeah, new technologies that might come along, or things that are expensive now coming down in price. We want to pick up those kinds of things and adjust. I'm hoping that the actual climate data is not changing that fast, and we've been using the TMY3 data sets, which I think they're at least 10 years, and I suppose if the government was to come out with like additional climate data, or forward-looking climate data, we could consider using that. We don't have we don't have resources to do our own studies on that.
Great. Thank you very much. Thanks to everyone who stuck with us through the technical difficulties. I hope to see everyone in Chicago this September for our annual conference, the 10th annual to be exact. Graham, any final
Me
words?
too. Thank you for listening, and I hope there were at least a few people from the Building America side of the house this time.
We'll look into the attendee list. I hope everyone enjoys the rest of their evening.